I'd like to talk a little bit about the origin of magmas, that is, the molten rock that's feeding these volcanoes. Let's first look at where melts are generated. And we've talked about several of these environments. We've talked about subduction zone volcanoes, and those include the island arcs where you've got ocean-ocean collision zones, or ocean-continent collision zones, as in the Andes or elsewhere where you have oceanic crust colliding with a continent. Those subduction zone volcanoes produce a lot of magmatism. This graph is broken up into two parts. It shows the intrusive part of the magmatism, or the melts that are intruded from the underlying mantle wedge. And the vast majority of what's intruded is actually intrusive rock, and so that crystallizes as plutonic rocks, whereas the amount of the volume of rock that's erupted, or lava that's erupted, or other pyroclastic material that's erupted, is a very small percentage compared to what is left behind and crystallized underground. But that is actually much less than where the vast majority of magmatism happens on Earth, and that's at the mid-ocean ridges. So at the mid-ocean ridges, where we have partial melts of the mantle rising up and then erupting as basalts and forming the oceanic crust, again, most of what is generated in terms of melt at mid-ocean ridges is crystallized and cools under the surface of the crust. So it's actually plutonic or intrusive. And it's a small percentage, or a small percentage of the total volume that's actually erupted as basalts. Now, if we consider the other kinds of volcanism, those would be oceanic intraplate volcanoes, so ocean hotspots, or continental intraplate volcanoes, so continental hotspots. So this is like Yellowstone is a continental hotspot, and Hawaii is an example of an oceanic hotspot. Those are relatively small fractions of the total volcanism that's taking place globally, particularly compared to, even compared to subduction zones, but obviously the total is tiny in comparison to the subduction zones and mid-ocean ridges. Now, if we look at the total volume of magmas that are erupted globally, again, you'll see the vast majority in this chart shows that it's happening at rift zones, so those mid-ocean ridges, and then a smaller percentage is happening at the intraplate volcanoes and subduction zones. But compare that to the historic eruptions that we think of when we think of volcanic eruptions of note, and those include mostly subduction zone volcanoes, so eruptions of the Alaskan volcanoes, Mount St. Helens, Krakatoa, Toba, some of the other, Vesuvius, those that we know of, those are all subduction zone volcanoes, whereas the intraplate volcanoes and the rift zones are producing a much smaller percentage. So we don't see a lot of, obviously, the magmatism that's happening in the rift zones because it's underwater for the most part. Now, looking more closely at how melts are generated in subduction zone volcanoes, again, I'll point out that most of the subduction zone volcanoes are around the rim of the Pacific, or this ring of fire. And these are subduction zones where the Nazca Plate or smaller plates are subducting beneath the continental margins of South America, North America, or Eastern Asia, and in Malaysia and Indonesia. I showed you this diagram before, but this is more, I'll go into some more detail. This shows oceanic crust, and that is this package of rock that is subducting down beneath a continent. So this is the continent. This is the oceanic crust. I'll abbreviate. What you're seeing is, what's represented is that you're taking the basaltic oceanic crust down to great depth. When you do that, you are bringing along with it sediments, hydrous sediments, so sediments with lots of water in them, hydrous minerals that are actually in the crust, subducting them to great depths. What happens is that then you metamorphose the oceanic crust, and many of those hydrous minerals, or all that water that is subducted, dehydrates, and the water enters, because it's buoyant, enters the overlying mantle wedge. That's this wedge of mantle right here. That's your mantle wedge, just because it forms a wedge shape beneath, above a subducting crustal block. The water enters that mantle wedge, and it reduces the melting temperature of the mantle. So normally this mantle here in purple would melt at very high temperatures. So this is actually solid rock that's beneath the continent, or that's in the mantle wedge. This is solid. It's crystallized. But when you take the fluids, remove the fluids from the subducting crust and sediments, and those enter the solid mantle above it, it reduces the melting temperature. So whereas if it melted at the same pressure or at the same depth within the earth, normally at 1600 degrees or 1400 degrees, it might be reduced to 1200 degrees or 1000 degrees. So you're able to melt what was formerly solid rock. And what that does is, when you melt it, it generates partial melt. So it's a small percentage of melt of the mantle. And these are basaltic melts. Even though the mantle wedge is ultramafic, this is the purple mantle wedge is ultramafic. When you partially melt it, you get basalts. Basalts then rise into the overlying continental crust. And the continental crust is, on average, it's intermediate in composition. So we'll say it's approximately andesite. And what ends up happening is that you're changing these basaltic melts and incorporating pieces of continental crust, or changing the composition of the basaltic melts by either partially crystallizing them or partially melting other rocks. And what you end up with is this intermediate composition continental crust. And what is erupted at these ocean continent arc volcanoes is generally intermediate composition. So what's happening is these steps are outlined here. Downgoing oceanic slab is hydrated, it has water in it, it undergoes metamorphism and dehydration. Those fluids enter the overlying mantle, it reduces the melting temperature of the mantle, and you get partial melts of the mantle, and that's what produces the arc magmatism at these oceanic continental arcs. Now, if we move on to mid-ocean ridges, again, here's a map of the mid-ocean ridges. And you'll see that mostly we're talking about the Mid-Atlantic Ridge, the ridges going through the Indian Ocean, and into the Eastern Pacific. I showed you this image before as well. What we're seeing here is the ridge axis, which is where the partial melt of the mantle again, partial melts of the mantle, are rising up and being erupted as basalts to form oceanic crust. And by adding new material, we're pushing the two plates on either side of that plate boundary, on the other side of that mid-ocean rift, apart, and spreading it open and creating new continental crust. What if you draw a simple cross section? What that might look like is rising partial melts of mantle into the area beneath the ridge axis, right there, creating new basalts. These are basaltic eruptions, and pushing the plates apart as you create the new crust. What it looks like in some more detail is, and this is looking again at the same kind of cross section at the ridge axis here, you have a zone of intrusion beneath the ridge axis, or those partial melts of mantle, and you have the volcanic layer, which are the basalts. Beneath that is a sill-like magma body. Okay, so this is 1 or 2 kilometers deep. Sills are vertical intrusions that are feeding the basaltic eruptions from a partially solidified zone. So they're partial melt still down there. So it's a crystal mush. That's what this is showing on the diagram. So there's this crystal mush that has crystals in it. It feeds these dikes, these vertical dikes, that end up producing the basalts on the ocean floor. And beneath that is a solidified, or beneath these sheeted dikes is solidified and hot gabbro. So this diagram really shows you that the vast majority of the magmatism that's taking place at the mid-ocean ridge is ending up being the intrusive gabbros, the plutonic basalt equivalents, and a much smaller percentage of actual basalts that are erupted onto the surface. We look at intraplate volcanism, and here's the map again showing the various hotspots and their traces on the plates. We'll look at that system. I showed you this before, describing the mantle plumes coming from this core mantle boundary area, and the plumes rising up to the base of the lithosphere. And so we move over here and see this plume rising up from the core mantle boundary. We'll abbreviate that core mantle boundary. That's where it's coming from. And then ponding and spreading out at the base of the lithosphere, and then feeding the volcanoes at the hot spot. And so there's some volcanism that's not directly at the center of the top of that mantle plume, but off center. We look at a slightly more detailed view of what's taking place. We'll see that there's a zone of partial melting starting off beneath, if we imagine this is Mauna Loa, a zone of partial melting at around 100 kilometers depth. And here, the magma is ascending through a conduit system. So you can imagine not a round spherical blob of magma, but several conduits, feeder dikes, maybe, several places where melt is rising up in a anastomosing sort of way toward the surface. And then when it gets to near the surface, there is some sort of ponding. It's a magma reservoir near the summit. And then there are eruptions off center along these rift zones on the flanks of the intraplate volcanoes. If we look at continental rift zones, and I'll remind you that the Basin Range is this area of valleys and mountains that form these broadly north-south ridges and valleys across western North America. That's that's our nearest continental rift zone. Farther abroad, we have the East African Rift Zone, where it's not, these aren't plate boundaries, but perhaps protoplate boundaries, but where there's spreading starting within a continent, and volcanism and magmatism beneath it, and volcanic rocks being produced in those rift zones. This process is most similar to what's taking place at the mid-ocean ridges, in that we have thinned crusts. So over time, these intrusions, we start up at the top here, if we label these 1, 2, 3. We start off with an intrusion, and the buoyant partial melts helping to spread the crust and thin the crust, so it gradually becomes thinner. So if we move down to number 3, you'll see that in the end the crust is much thinner near the center of the rift than away from the rift. That thinned crust means that there's a lot of overlying lithostatic pressure, so the pressure of the overlying rock is reduced because the crust is thin. And what that does, that has the effect of reducing the melting temperature again of the underlying mantle. And so we decompress the mantle and we can melt it. Another area, we haven't really talked about this. This is the Himalayan Tibetan Plateau is an area where we have a continent-continent collision. It's also a convergent plate boundary, but it's somewhat unusual in that we have a continent, in this case it's India to the south and Asia to the north, that collided some 55 million years ago. And that has produced the Himalaya mountain belt to the south of this high topography. And then the Tibetan Plateau, that's this region of very high topography. This plateau, this whole area in here, is essentially doubly thick crust, because it is where India has subducted a very shallow angle beneath Asia. So we have Asia to the north here, Indian crust to the south, and the Indian plate is being subducted at maybe 10 degrees beneath Asia, and here's the contact as it goes down. And this has thickened the crust so that instead of a normal crust in a craton sort of area is going to be maybe 30 kilometers thick. The Sierra Nevada might be about 50 kilometers thick, but the crust beneath the Tibetan Plateau, beneath the Himalaya, is down to perhaps 70, 80 kilometers thick, And so it's extremely thick beneath the plateau. And it's essentially two continents stacked on top of one another. And what happens in that case is that you have an intermediate composition Indian plate and an intermediate composition Eurasian plate. And so you're stuffing continental crust down to very great depths. That continental crust is more hydrous than other crust, than oceanic crust, and it's more felsic. And the result is that when you get metamorphism of this intermediate composition crust, a similar process happens as to what you get when you subduct oceanic crust. You get dehydration of the rocks, and the water enters the overlying rock and lowers the melting temperature and generates new melts. And that's what these pink rocks are labeled as. They're very felsic rocks. They're actually called leucogranites. It means that there's very small percentage, less than 5% mafic minerals or dark minerals in these granitic rocks that result. So it's a very felsic melt that's generated when you melt continental crust. And so that's another way that you can produce magmas at a plate boundary that we haven't yet talked about. So finally, I'll show you this diagram, which is not so simple, but let's take it one step at a time. We've looked at melting at hotspots, mid-ocean ridges, subduction zones, both ocean-continent and ocean-ocean, and continent-continent subduction zones, and we've looked at rifting in mid-plate. These all of the magmatism and all of these plate and intraplate zones result from just a few mechanisms for melting. So the origins of the magmas for partial melting of mantle or continental crust all result from either an increase in temperature, where we've got hot spots being generated from particularly hot places along the core mantle boundary, generating those mantle plumes. We have places at continental rifts and mid-ocean ridges where we see a decrease in pressure, or generates decompression melting, so reducing the lithostatic pressure on the mantle, reduces the pressure on the mantle, lowers the melting temperature of the mantle, and that gives us the partial melts, or the basalts, at mid-ocean ridges and continental rifts. Or we can add fluids. There's another mechanism, and that's what we see happening at subduction zones, where fluids being driven off of the subducting oceanic crust enter the mantle wedge, lower the melting temperature of the mantle wedge, and produce partial melts or basaltic melts that rise up into the overlying crust. Or where we have thickened continental crust like the Himalaya, we see the anatexis taking place. So that's fluids being driven off by metamorphism in continental crust and then generating these very felsic melts. So those are the ways that you get melts and the mechanisms that you get melts by. And this diagram here is trying to explain that. We might need to go over this in class, but let me just try this. What we're seeing is temperature on the top axis. We see depth on the right going down. We see the corresponding pressures in gigapascals on the left that correspond to those depths. And what we're seeing is in this red line that I'm going to trace over in blue is the geotherm. And this is the geotherm for the mantle. So the peridotite is an approximation of a mantle rock. So the geotherm is simply how temperature increases as you go down into the mantle. So we're starting off at zero pressure, so zero depth, and going down to 50 and then 100 kilometers deep. And that's what just from conductive heating from the core of the Earth, mostly conductive heating, is heating up that mantle with depth. And we see, let me erase that to simplify things. We see this white line, this white dashed line, is the dry melting curve. This is the line that you would have to intersect a particular, so the mantle would have to be at a temperature at least of this, at this white line, or a higher temperature at a given depth in order to melt the mantle rocks. So if you were at 50 kilometers depth, the mantle would have to be about, let's call that 1300 degrees Celsius to melt. It has to be at least 1300 degrees Celsius. Peridotite has to be to melt. So that's if you have dry peridotites. This is the dry melting curve. So if there's no water whatsoever in the mantle rock, that line defines where you get melting at higher temperatures. So melting or no melting at lower temperatures. Now, look what happens if you add water. That's the red line, this red dashed line here. So you add a little bit of water, and I don't see how much water, but we're probably talking a very small percentage, maybe 1% or less, but a little bit of water, and the melting curve for the peridotite, so this is the wet melting curve instead of the dry melting curve, that shows that the melting temperatures for the peridotite are at much lower temperatures than if the peridotite was dry. So here's the dry curve, here's the wet curve. So the temperatures that correspond, the temperature at 50 kilometers is, for the wet curve, is maybe 1100 degrees Celsius. 1100 degrees C to melt a peridotite. So it's 200 degrees Celsius colder mantle to melt it at the same depth. And that's what I'm trying to describe as far as adding fluids at a volcanic arc. So the subduction, in a subduction zone, the subducting oceanic crust metamorphoses, drives off water from those reactions. The water enters the overlying mantle wedge and lowers that melting temperature for the peridotite. And then because that melting curve intersects the actual temperatures that the rocks are at, if we follow the geotherm, then we can see melting where they intersect starting at around 45 kilometers depth. So that's telling us that basically the upshot is you add water to the mantle peridotite, lower its melting temperature, and that intersects the normal geotherm, and you should be able to melt mantle as long as you add water.